Welcome to this lecture series in linear algebra. We have started our discussion on determinants, and to further the discussion we will need to understand the notion of permutations first, and this and the next few lectures will be about that. So let's get started. We don't have anything to recall or anything. This is a completely basic lecture. So first let us define what is a permutation of a set X. Okay. So a permutation of a set X is, by definition, any bijection or is a bijection of X with itself. Okay, so it's a very nice definition. What is it doing? It is permuting the things in X. Think of X as a, let's say, 3-element set for the moment, and let's say it is the first 3 natural numbers. So you could send 1 to 2, 2 to 3, and 3 to 1. So you've permuted the things here, and that's what this definition is capturing. Here we don't even require that the set X be finite, even though we will only be interested in finite permutations of finite sets. Alright, so I hope this terminology is justified in your mind. Why do we call such a thing, such a bijection, a permutation of X? It's because it is just relabeling the things in the set X, and if you think of X as some ordered thing, then it will look like a permutation. You have replaced the positions, you have changed the positions of the objects in the set X. Anyway, so that is the definition. And what is the notation? The set of all permutations of a given set X is denoted by the symbol SYM X. So this stands for symmetry, and the root of that word comes from group theory, but for us it doesn't matter, it's just a notation. In some texts, you will also see this notation, S and then a subscript X or something else. Note that if the size of X is n is some positive integer, so X is a finite set and it has size, suppose, n, then the size of this set is n factorial. Very easy to see, basic combinatorics. And a point of notation again, if n is a positive integer, then we may also write S sub n to denote symmetric group. I shouldn't call it symmetric group, the set of all permutations of the first n integers. So this is just a more convenient notation than that. Alright, so just so much for notations, but let's see examples. That is most important. Any definition in mathematics has to be understood via examples, and any theorem in mathematics also has to be understood via examples as much as possible. Okay, so first example is fix any set. And when I say a set, I mean a non-empty set, because otherwise you can't do anything. So then the identity map is a permutation. It is the trivial permutation. Trivial because it is not doing anything. It is keeping the thing where it was. It sends little x to itself. Right, so the identity map is always there. So every set has a permutation. Okay, not very interesting. Second example. This time you take x as the first 3 integers, first 3 natural numbers, and define sigma. Generally, permutations are denoted by small Greek letters, sigma, tau, theta, etc. So what is the definition? The way we define it is send 1 to 2, 2 to 3, and 3 to 1. This is another example of a permutation. Okay? And now for a more generic example, suppose X is any set. Could be an infinite set, doesn't matter. And let A and B be 2 distinct elements in it. Okay, then we can define a permutation tau as follows. Tau x is x if x is not equal to a and x is not equal to b. So we do not disturb anything apart from these two things. If x is not a and not b, then just keep it as such. But if x is equal to a, then send it to b. And if x is equal to b, then send it to a. So pictorially what is happening is, let's say this is our set x. This is a and that is b. What we are doing is tau sends a to b, b to a, and keeps everything else fixed. Such permutations are going to have a special place in our discussion. First of all, verify that this is indeed a permutation, very easy to verify. And these will play a special role in our discussion. These are called transpositions. We'll get to them. All right, so now let's move on. So here are some facts about permutations. Will not take much time. So fix any set, again non-empty set, and suppose sigma and tau are two permutations of x, then their composite is again a permutation of x. And here is a pictorial way of depicting the same thing. You have tau takes x to x, sigma which again takes x to x. Sigma composed with tau is just this map. First you apply tau, then you apply sigma, this map. So, and since sigma and tau are bijections, the composite is also a bijection and hence a permutation of x. Very simple observation, so the proof, if you really want, is an exercise. Nothing to prove here really, but yeah. There is one line that you may want to write if you haven't done this kind of thing before. And similarly, there is this very simple lemma again. Fix any set, fix a permutation of it, then the inverse of it is also a permutation. The inverse makes sense because sigma is a bijection. Every bijection map has an inverse. And the inverse is also a bijection. So there's nothing to do here. This is also clear. Fine. So every permutation can be inverted and two different permutations of the same set. Two different permutations or even the two same permutations also can be composed. In fact, this is read many times as multiplication. You're multiplying sigma and tau, and this perspective of multiplication is taken in group theory. Anyway, doesn't matter. Now, there's this very nice way of depicting a permutation, which I call the permutation digraph. Certainly, this must have a name in the literature, but I did not check. Maybe this is the name in the literature that it goes by. Anyway, so suppose we have this permutation of the set 1, 2, 3, and this is one way to depict it. So it sends 1 to 2, 2 to 3, and 3 to 1. We can depict the same data via a graph, a directed graph. So you don't need to know anything about graph theory or anything. We can just follow along. So what does it do? It sends 1 to 2. So we'll draw an arrow from 1 to 2. It sends 2 to 3. So draw an arrow from 2 to 3. And 3 to 1. So this graph is capturing the same data as that, and admittedly this looks much nicer. Okay, next one. Here it's a permutation of first 5 natural numbers. 1 to 3, 2 to 5, 3 to 4, 4 to 1, and 5 to 2. Let's draw the graph. So 1 goes to 3, 3 goes to 4, or maybe let's first do 2. 2 goes to 5, 3 goes to 4, 4 goes to 1, and 5 goes to 2. So here I should make, so that is the permutation digraph. But I want to separate it out a little bit. So note that we can have these two disjoint components, so to say. We can depict it that way. So it's kind of messing around 1, 3, 4, and separately it is messing around 2 and 5. These two are in some sense parts of sigma or components of sigma. When we study cycle decomposition of a permutation, this is exactly what it is anyway. So this is the permutation digraph of this guy. And lastly, let's talk about this one. So 1 goes to 3, 7, 6, so on. So let's just draw this right away. 1 goes to 3, 2 goes to 7, 3 goes to 6, 4 goes to 5, 5 goes to 2, 6 goes to 1, 7 goes to 4, and 8 is fixed. Nothing happens to 8. So you may draw a cycle like that, but it is better to just leave it alone. The points which are fixed, don't do anything to it, just make it, lonely. So here also we can separate out and make it look much nicer. So let me try to do that. Right, so there is this 3 cycle, there is this 4 cycle, right, and there is this singleton. This 4 cycle we can make look a little better, because it's just better to draw 5 above and 4 below. So let me change the labels and change the arrows. No, this is not correct. 2 goes to 7, 7 goes to 4, oops, 4 goes to 5, and 5 goes to 2. Yeah. So again, we see, just like in the previous one, cycles appeared, disjoint cycles appeared, and even the permutation digraph of this bigger one also has the same kind of property. So in fact, this is a completely general thing. Any permutation of a finite set, if you make the permutation digraph of it, you will see disjoint cycles in it. You may see a big cycle also which contains all the vertices. That's okay. But what will not happen is that you will get some, 2 different cycles interacting in some way. That's not possible. So that is the next proposition. If you have a permutation of a finite set X, then the digraph of sigma is a union of disjoint cycles. Right, so when I say digraph, we just defined what's a permutation digraph. We didn't give a formal definition, but I'm sure it is clear what we mean. And the proof of this I'm not going to write down. You can take this as an exercise, but all that is happening is the following. Every vertex in the digraph sends out one edge and consumes one edge. So just with that property, you can show that there has to be just disjoint cycles. Because you just keep moving. At some point, you have to revisit what you've already visited, because the set X is finite. And those are precisely the cycles. Of course, you will be using the bijectivity of sigma in this argument. Okay, so so let me just stop here with this lecture. Very, very basic things we discussed. We will continue our discussion next time. All right.